Hey look, it's Paper Cam, way with the future. So I want to encourage you to mess around with math. Ask yourself questions, even if they seem weird, and see what you come up with. So here's the old Pythagorean Theorem, right? You can use it to check if this is true. If a triangle can exist like this. So we check it out. We get 9 plus 16 equals 25, so it works. This is a valid triangle. If one of these sides was missing, we could use this to figure out what the other side was. Now, this will often be illustrated in books this way. You've probably all seen this drawing. And that makes sense because we're squaring these. So we're taking the quantity 5 times 5, 3 times 3, 4 times 4, and we're seeing that if you add these, you get this. That's all fine and good. What if we do this, though? What if I say, what's so special about squares? Actually, I'm bored of squares. How about we do half circles? Poorly drawn half circles. Will this still work? So I'm going to just try it for this number case first. So the radius of this is 5 over 2 because we want pi r squared to get this, and then we'll put it over 2. But maybe we won't bother putting it over 2. We'll see. So the radius is this. So that we're going to have something like this. Pi times that squared. That'll give us, the area of the whole thing. But because it's only half of a circle, we'll do that. And then I've got to check if it's going to equal, with a little question mark, these other ones. So pi times 3 over 2 squared over 2 plus pi times 4 over 2 squared over 2. Now, I'm noticing that if I multiply a 2 by both of these, it will go away, both sides of the equation. So we can't ignore it, like I was saying. And then, look, I can divide both sides by pi if I want. Those will go away. So let's just do the fractions like this for a moment. Right? I just, in case this is confusing, for this, I just did 5, 2 times 5, 2, because it's this squared. But then I didn't bother calculating what that product is. I just wrote it like this, because I could see ahead of time that, I can cancel those out by multiplying both sides by 2 to the second, which is 4. And then I get this, which I already knew was true from before. So it worked for 1, but will it work in general? So if I let's just relabel these to make life a little easier. One time in a math class that my teacher filled up 3 blackboards with this enormous calculation, and then he realized it was wrong. But somebody, or no, he said, oh, but it's actually, this is all linear and it'll just be off by a factor of this. So if I just adjust right here, and then he fixed it in about 20 seconds, and we gave him a standing ovation. It was so exciting. This is not as exciting, but you can see I'm just testing it in the abstract now. So if these were C, A, and B, I would have written this, and everything would have canceled down, and I would have gotten this again, C, A, B. So it would have just reduced back to the original Pythagorean theorem, which we already know is true. But ask yourself, what if this was the one you learned, and then we checked this one? Like, what's so special about squares? And how about this? What if I decide A, B, C? What if I decide, ooh, I want to have equilateral triangles here instead of squares or circles, right? So these sides are all like this. Sorry, these would be C's. And these will be A's, right? Will this just be equivalent to the original Pythagorean theorem? What if you put octagons or pentagons on the sides? Try it out and see what happens. See if you can figure out if it will always be true for any shape you put here. And have fun with that.